Alrighty, I'm gonna go ahead and get started. So it is February 18th, and here is this week's CSCE 312 Sunday review. So first off, I just want to talk about a few things from last week that I ended up not going over, but then I talked about it a lot in my lab and like explained it there. So I thought I'd just go over it just to make sure that we're all on the same page with timing diagrams for flip-flops and registers. So this is a flip-flop, as we know. This is the flip-flop clock or timing diagram. So, because this was big questions, um, this is the clock. This will be given from input. This is not something you have to come up with. If you do have to come up with a clock, literally just draw this, because that's a clock. That's a clock. D/DM, this is the input. This is going to be the same, which is why this is the same. CM is the clock on the master. If you see here, this is where the clock comes from. The clock on the master is actually the opposite of whatever a clock is. And the clock on the servant is just the regular clock. This is a NOT gate, not some other module. There were some confusions there. So clear that up. So we have clock here. We know that clock is going to be this opposite of CM. So whenever clock is down 0, CM is up 1. CS is going to be the same as clock, so we can just copy that down. D/DM is the user input. So that's not, if you were to make one of these diagrams, you would be provided at least this, because how else are you going to know what the rest works without having the input? So when D/DM, the input is clicked on, it is while the clock for the master is also on, because it's opposite of clock, and therefore it's going to store that value in QM, which is the master latches output and the servant latches input. So see, we have that slight delay here. That's why we have this little arrow, slight delay of time chunk. And then it stores that value 1 into the master. Then when the clock turns on for the servant, as it does right here, we have another slight time delay where that, because this is 1, it then gets stored as 1 in the servant, and then the output of that, so QS, this is the output, which is also Q, will be 1. Cool. So I don't want to spend too much time on this because I'll talk about the register. So register is also a lot simpler than, in my opinion, it's a lot simpler than the flip-flop diagram. So for a register, when the clock goes on, it stores the value that is currently in your input when the clock is flipped into the first register. So this is for example, a three registers connected to each other. So on the first clock, it stores it in that first one. It won't store it in this 0 because it is already passed by the time this clock delay happens. So when I guess it's supposed to be 18. 18 gets stored here, and then on the next clock cycle, it'll store it in the next register down and store whatever's here in its register. So it shifts that value to the next register and gets a new one. And it just does that continuously. You can just think of it as a diagonal when the clock hits. Cool. So today, the new stuff we're going to talk about controllers, data path components, and 2's complement. So controllers are things that help us control data input. Components are things that store and transform data. So those are your adders, shifters, etc. And then 2's complement is a way to represent negative numbers in binary. So first off, we're just talking about some different types of registers. I talked about registers a bit at the end of my last review, but a shift register is a register that holds these values and then shifts them one position right and puts a 0 in the leftmost bit. It doesn't transfer over, or it doesn't carry over. So these go here, and then instead of having it carry over like this, that does not happen, and instead just gets a new 0 number here. A rotate register does actually move that bit over. So you can see this bit goes to the beginning and everything else shifts right. This is just a right arrow. Sorry. And then we have a multifunction register, which is many registers together that have multiple functions. So not only can it shift right or left, it can also load things in, maintain their values based on this S1, S0 input. Okay. So if you have a multifunction register, you're going to need a register operation table like this. And to determine it, this is basically going to have a mux attached to it, like a mux that I talked about last week, where it's going to choose based on the input, the binary input, it's going to choose from one of those options. So if it's 2 bits, you're going to have 4 options, 3 bits, 8 options, etc. And then it uses that mux to map to control and tells it what to do. Okay, next up we've got adders. So a half adder adds 2 bits together. This right here is the half adder. This little block here. So it'll add these 2 input bits together. This will be the sum of those 2 bits, so 0 and 1. The sum is 1. And the carryover is 0 because there's nothing to carry there. This is a full adder. It has 3 bits that it generates the sum for. So 0, 1, 1. Sum is 0 because those get added together, and then the carry is going to end up being 1. So these 2 together, this whole chunk here, so this is the full adder, sorry, makes up a carry ripple adder, which is able to basically do addition like a human would. And so this combination of the half and full adder can build any size carry ripple adder. And then this is a cascading adder. It's just a bunch of adders put together. So this is the half adder, and these are all full adders. So carry ripple. But it continues in a sequence to add multiple things together. So you could add these 2 numbers together and then add these numbers to that number, et cetera, which is why it's called a cascading, because it adds it in sequence. I didn't get rid of my annotations. Wow. Okay, these are shifters. So shifting just means moving every bit either right or left. This can be really helpful because if you move every bit left, that's the same as multiplying by 2. If you move every bit right, that's the same as dividing by 2 because of the way binary works with the 2 to the n. Super cool. So that's a shifter. This does both right and left shifting. And then a barrel shifter is this thing here. It's a shifter that can shift any amount using 3 chain shifters. So if you want to shift by 8, you can put in your input that you want to shift by 8 and it'll shift it that amount of times or not 8, but like if you have an 8-bit number and you want to shift it by 3, it can do all 3 of those shifts for you. So it's super useful for doing different types of input rather than just shifting right or left once. Okay, comparators. So this is an equality comparator. All it does is output 1 if the 2 numbers that are inputs are the same. And so what it does, so this is the numbers 0, 1, 1, 0, and 0, 1, 1, 1. So as you can see, these 2 bits are the same. So you get the 1, these 2 bits are the same, 1, these 2 bits are the same, 1, but these 2 bits are different, which gives you a 0, and when put into that AND gate, the whole thing is 0. So you know that the numbers are not equal to each other. A magnitude comparator is basically just a hyped up version of an equality comparator. So it can compare equality, but it can also indicate which of the inputs is larger. So there will be an output if the A is larger, there'll be an output if the B is larger, and if they're the same, etc. And it's just built in stages like this, which is pretty cool. I'm not going to go over too deeply how they're made because you will have a lab where you'll be making them yourselves, but it's all in the slides that you can look at the structure more closely. Okay, so counters, exactly what it sounds like, they help count. So a counter is, an incrementer is made up of half adders. The thing we talked about before that has a sum and a carry. So sum, carry, and all it's used to do is increment the input number by 1. Pretty simple. A subtractor is a bit more complicated, and it is kind of similar to a carry adder, how a carry adder, you can mimic how humans would do addition by hand. It basically does that for subtraction. So it's like a carry adder, but with taking things away. Or yeah, carry. Okay, and then the last big topic I want to talk about for today's Sunday review is 2's complement. So 2's complement is the only real way that you're going to be able to encode negative numbers in binary and when you're working with bits and wires. So to take a number from positive to negative, originals to 2's complement, all you have to do is invert every single bit and then add 1. So as you can see, 0 goes to 1, 1 goes to 0, all the way down bit by bit, and then you add 1 to the last, or to the first, to the 0th bit. So in this case, there's already a 1 here. So what we have to do is we add the 1 and then we carry this over, because basically what happens is it's like you're doing an addition by 10, but your max is 1. So when you get 2, so if you have this and you're adding 1 to it, this is 2, but you can't put 2 here. You can only put 1 here. So you have 1 here and then you split the other 1 here, and then it carries down. Okay. So then you get this final 2's complement number of 0, 0, 1, 1, 1. Say this is, if it was another example, if this was 0 instead of 1, and this was 1, what you would have to do is you would have to carry the 1 all the way over to the next 0. So this would end up looking like this instead. So that does have some faults. Say it ends up being a 0 here, and this ends up being a 1 already, and you have to carry, these are both 0. These are 1s already, and you have to carry it all the way over here. That could overflow. So you have to have some sort of backup in case of an overflow. Which is also something that you will have to deal with in labs eventually. Yay! Okay. So that is everything that I had to go over today. It's not as much as previous weeks. You're basically just learning about different types of modules that you have available to you or that you could potentially learn how to create, which is super fun, super cool. You will be making shifters and adders for sure in the upcoming weeks. So I just want to let y'all know I will not be able to host Sunday review next week. I will not have Wi-Fi, be out of the country. So I will do double the amount when I come back the week after. So I'll take questions now. Thank y'all.